Hey, in this video, I wanted to go over the answers to the solutions, acids, and bases section of the review packet. So first of all, just some general characteristics of acids and bases. All right, remember acids tend to have sour taste, bases tend to have bitter taste. All right, many acids will react with metals. All right, if you have base, if you were to have, like, for example, sodium hydroxide solution, which is a base, that solution feels slippery in your hands, all right? And acids would be what turn litmus paper red. By contrast, bases would turn red litmus paper blue. Some pH problems. All right, so for strong acids or bases, all right, and HCl is a strong acid, whatever the molarity of that solution is can be considered to be the same as the hydronium ion concentration. And that's because this is a strong acid, so all of it is going to break apart when you put it into water. All right, so every little bit of that of this gets turned into H3O plus. So we could assume that this is the molarity of the H3O plus, and then we're just going to plug that into the equation for pH, giving us this pH, and then we can turn that into a POH. All right, so for this particular material, we could assume that that is acidic. All right, and again, there's a couple ways you can figure it out, but I always just look at the pH. If it's less than 7, it's going to be acidic. All right, for this problem right here, what's the molarity of this KOH solution? All right, so the molarity of the KOH is going to be the same thing as the molarity of the OH, OH minus. All right, so we can actually turn that into, so since that's the molarity, we could say that the molarity of the KOH is going to equal the same thing. All right, I'll go over how we calculated that in just a second. All right, the way that we do that is by, first of all, recognizing that the pH is 9.5. We can turn that into POH, all right? And the POH, if we know that, we can calculate the hydroxide ion concentration. All right, the way that you do that is you, once you get to this point right here, you change the signs. All right, so I'm going to put a negative there and turn that into a positive, and then I'm going to do 10 raised to on both sides, and that's going to give me this number right here. And since KOH is a strong base, I could assume that the hydroxide ion concentration is the same thing as the concentration of KOH. All right. So when you're doing an acid-base neutralization, when you get that neutralization, when you've added just enough acid or base to neutralize the acid or base that's already there, when you're doing that, at that point, it's going to be considered the equivalence point. All right, that's when it's fully neutralized. So you could assume that the pH of the solution right here at the equivalence point is going to be neutral, and that's going to be true as long as you're neutralizing a strong acid with a strong base. We don't do examples of weak acids with other types of bases in this course, so just, you know, for the purposes of this course, just realize that at the equivalence point, it's going to be neutral. All right. For this problem right here, we're doing a neutralization. Here is the neutralization reaction. All right. It's the coefficients are 1 to 1 to 1 to 1. All right. What I'm going to do first is I'm going to figure out how many moles of HCl there are in this solution right here. So I can plug that into our molarity equation, and that's going to tell us the number of moles of HCl. All right, and I can take that number of moles of HCl and I can put that into a crossbar to figure out how many moles of NaOH would be required. All right. And next, now that we know the number of moles of sodium hydroxide and we know the volume of that solution, we can use this equation right here to calculate the molarity of that solution. All right, so just plugging that in, we would get this value right here. So that would be your final answer. All right, you should know the following vocabulary, like hydronium ion is H3O plus. When they talk about hydrogen ion, they would be talking about H plus. But remember, H plus doesn't really exist in water, even though people will still talk about it as if it does. When they say H plus, you can consider it to be the same thing as H3O plus. All right, hydroxide is OH minus, and these things are both very important when you're talking about acids and bases, because that's what gives water its pH. All right, strong acid or base is a material that an acid or a base that fully dissociates in water. All right, weak acids are going to be acids that only partially dissociate in water. All right, so for example, if you had a strong acid, if you had 100 of those acid molecules and you put them into water, you would generate 100 H3O pluses. All right, if you had a weak acid and you put 100 of those molecules into water, you would only generate a few H3O pluses, because not all of it breaks apart and reacts with water to make the H3O plus. All right, titration, we didn't talk a whole lot about this in the class, but titration is the process by which you neutralize, by which you determine the concentration of an unknown acid or a base by measuring the amount of a known concentration of acid or base to that in order to neutralize it. All right. So when you're doing titrations, you can have, when you're done with it, when you have completely neutralized your acid or base, you will be at what's called the equivalence point. All right, for solutions. All right, a couple basic questions. How many grams of aluminum chloride would be required to make a 2.25 molar solution in this much water? All right, so the first thing that we're going to do is I'm going to take this molarity right here, and I know the volume of it, so I can use this equation right here to calculate how many moles of aluminum chloride that would be. All right, but the question asks us how many grams, so we can do a one-step crossbar to calculate the number of grams. All right, the next question is the dilution problem. All right, we can use M1V1 equals M2V2. The thing that we don't know is the original volume, so we're going to calculate these, put these values in, and we end up getting this value for the volume. All right, another molarity problem right here. It gives us the number of moles, the number of liters, and we can calculate the molarity. All right, notice, remember with molarity, you can either give your unit as moles per liter, but you could also use capital M. All right, it means the same thing. All right, again, a molarity problem. The one thing about this is that we have to turn grams into moles. All right, remember the molarity equation uses moles. All right, so we can turn grams into moles by using this just a one-step crossbar. All right, notice I've got 4 sig figs in this because this has got 4 sig figs, this has got 4 sig figs, so I should round it at this point right here. All right, I can take that and put that into, so rearranging this equation right here to solve for volume gives this, and putting this value in here for moles, putting this value right in here for my molarity. Notice I turn that capital M into moles per liter. And by doing that, I can see the units that are going to cancel out there. I can see a mole there, mole there. Those would then cancel out. All right, and that's going to mean that this is my my volume. Notice that since this has only got 3 significant figures, that's why I rounded this one right here to 3 significant figures. All right. One last thing, know how to read solubility curves, like the ones that we had on the practice and with the test. For example, be able to determine whether a solution is saturated or unsaturated. Be able to determine how many grams of a compound could dissolve in a certain amount of water at a certain temperature. All right, that's it for this review, and good luck with that section.